Hello and welcome to another tutorial. We're going to continue our discussion on the HelloWorld application in Java and then compiling it with native image to native executable binary. We saw how to just quickly write the HelloWorld application in macOS, and I'm just going to quickly go through the output that you will see. And again, as you see, this output in the terminal is colorful. That's because I'm using Fish, which is a friendly, intelligent or interactive shell, and it allows coloring. So some terminals don't have the capability of coloring, but some other terminals, if they're intelligent enough, they can allow coloring. So I recommend you use either a terminal that supports coloring, like for example the default terminal in Linux supports coloring. If you're using macOS, install Fish, and then it allows very nice coloring. You see very colorful text, right? So the very first thing is starting compilation process, GraalVM native image, and we saw that in the most recent version, which was 22.1.0. It actually shows more information about which toolchain it's using to compile your application to native binary. And then it tells you the version information, GraalVM, and then performing analysis, information about classes. It tells you which classes your application requires, how many classes your application requires to actually be successfully launched. And we know that most of these classes are from the JDK, because chances are your application, in our case, was just one simple class file, which was a HelloWorld. So if it says that your application requires like 3,205, it means all of them come from the JDK, right? How many use reflection? How many use GNI? We will touch upon these topics later on, because we know that Java, by its nature, it's a dynamically, it has a dynamic class loading feature, or JVM is lazy loading, which means JVM only searches for a type, like a class, if your application requires it, right? And then reflection means at runtime you can reflect upon the features that the class has, which attributes has. And these, as I mentioned, reflections or even JNI access, native access, these are not very friendly with static compilation. Static compilation means you have a compiler, it analyzes your source code and compiles everything to native executable binary. So reflection becomes some sort of tricky thing, right? Because it's not a dynamic, there is no runtime, right? There is no JVM. When you statically compile to a native executable binary, it's just the operating system telling the hardware what to do, right? And then building universe, performing a static analysis of classes, including JDK classes, parsing methods. Parsing just means it's tokenizing and understanding the methods. Inlining methods. Inlining is some sort of compiler optimization, which means whenever, instead of calling the runtime, which is basically the operating system, to go to this particular address to invoke this function or method, it just copies the entire code into where the method was invoked. That's called inlining, right? That's a very old like compiler optimization. Usually if your methods are small or functions are small, inlining works best. If your methods are very long, then usually inlining doesn't really work that well, right? So the trick here is that actually it's one of the best practices in Java or in any programming language. When you're doing object-oriented programming, try to keep your methods as small as possible. Compiling methods. Now the methods, the code inside the methods is compiled to native files, hardware instructions, or the assembly code. And then creating image. Image just means the actual native binary. So what happens is that the compiler, the native image, compiles all the classes, and then there is a linker is invoked, and the linker puts all the binaries, combines all the binaries together and creates one image, one native executable, right? And it also tells you the size of the file, and we saw that when you compile your Java application to native executable binary, the size is relatively large. It's like 11 megabytes or so. And the reason is that there's a lot of stuff that has to be compiled from the JDK itself. And it tells you, for example, the code area required 3.96 megabyte, almost 4 megabyte, which basically includes, or basically consists of 33% of the final size of the image file or the executable file is just the code area. About 7 megabyte or 60% is for the image heap, that actual Java heap, right? We said that native image actually kind of compiles a dense or a compact version of the JVM, and we know that JVM requires a heap area, right? And then the 7% or 847 kilobyte for the other data. We know that JVM, when you launch it, right, it has a heap and it has a meta space. Meta space hold the information about static fields, for example, of classes, and the other stuff like meta information, all the stuff that can be used for reflection. And then in total, the size of the image is 11.7 megabyte. So top 10 packages in code area. Code area, again, this is basically where the classes are compiled to optimize native binary. And they all come from the JDK, not surprisingly. Java util, Java lang, Java text, Java util regex, com Oracle SVM GNI. So this is substrate VM. So this is related only to GraalVM, like the typical Oracle JDK or Open JDK. They don't have this substrate VM. Java util concurrent, Java math, com Oracle SVM core reflect. So again, this is part of the substrate VM, which is only particular to specific to the GraalVM. Java util logging, sun util local provider, etc. And then top 10 object types in image heap. 1.75 megabyte of byte array for general heap data, right? Obviously, we hold the data into bytes. 789 kilobyte Java lang string. 581 Java lang class. 484 byte array for Java lang string. And etc. Java util concurrent, concurrent hash map, $node. Node is an inner class. We know that the name of the inner classes is outer class $inner class. Java lang string array, char array, and then a lot of stuff, right? And then it tells you it took basically 0.9 second to do the entire things. And then product artifacts is HelloWorld, which is executable, and it also gives you a build artifact, which is a text file, which tells you what kind of artifact was generated. We said that the main use case of the native image is to create executable files, right? To compile your Java application to executable file, but that's not necessary. You can also compile your Java application to a static library or dynamic library, and we will see it in the future lectures. And again, it finally says finish generating HelloWorld in 27 seconds. And then because we compiled in our current working directory, and then the native image was put in the executable file was put in the current working directory, we just say ./hello world. And we said that in Windows operating system, you don't need to use ./ or // because in Windows, the current working directory is automatically added to the path environment variable. So you just say hello world. On macOS and Linux, you have to use because the current working directory is not searchable. It's not by default added to the path environment variable. Now we can actually do this. So let's go back to our Eclipse. So we had this my app, let's say, and then let's open a terminal here. So if I say my underscore app, it's not going to work because the current working directory is not by default added to the path environment variable. What this means is that whenever we type a name, my app, and then hit a space, the terminal and the operating system, they assume that this is an executable application. And if you don't specify a relative path or an absolute path, then the terminal and our operating system, they search into the directories that are on the path environment variable, right? And we know that the current working directory is not added to the path environment variable by default. That's why we give a relative path or an absolute path, right? You can drag and drop this, and this is the full absolute path to this executable file, and then we do it, right? So again, the reason in macOS and Linux we use .myapp because we are giving a relative path, otherwise the terminal cannot find it. But if I open up a terminal at my home directory and then open up the bash RC, let's see. So what I'm going to do actually in the path environment variable, right? What I'm going to do, I'm actually going, so here I'm adding the Java JDK bin directory. Let's also add the current working directory. So we want to tell the terminal that, hey, the current working directory is always added to the path environment variable. I mean, that's not what I recommend you don't do that, but that's something that you can always do, right? And then we go back to our terminal. Maybe let's close it and then open it, or you can source the bash RC again, but here I'm just going to open it and close it again. So so if we echo our path environment variable, and now you see the dot, which means the current working directory is added, right? So now if I say my_app, now you see the fish makes it blue, which means this is found, right? I don't need to say /my app. It still works fine. The fish shell makes it blue, which means this is valid. But I don't need to do that because the current working directory, I instructed the terminal to always add the current working directory to the path environment variable. So again, in Windows, this happens by default. In macOS and Linux, this doesn't happen by default, but you can always do it. So I'm going to comment this out because that's not one of the best practices. It's best to avoid this kind of, it's best to avoid adding the current working directory to the path environment variable. I mean, in general, whenever you launch a application, you want to always know which directory you're launching it from, right? Where the application is. Now, for some applications like Java, C, obviously it's easier to just type the name instead of give the full path. That's why we add this to the bin directory of the JDK to the path environment variable. But again, the best practice is to define the Java home, right? And then add the bin. So now this is very explicit that I'm running the JDK from whatever the Java home is defined. And later on, if you want to switch to another JDK, instead of changing the path environment variable, you just change the Java home environment variable, which is easier, right? So and then, for example, if I want to quickly run the Java from the GraalVM JDK, I just say Graal home, right? And then bin and then Java -- version. So it's best to be more explicit and then define this kind of environment variables so that they can always quickly use them. All right. Now, what we want to discuss now is the Linux. Again, Linux and macOS, very similar syntax in terms of how to invoke the native image, how to basically compile your Java application. One thing that is the reason I'm separating the macOS and Linux is that now, in macOS, when you install the Xcode app, all the required dependencies for the native image are installed. They're all there. You don't need to do anything else. But in Linux, you kind of need to install a little bit of more dependencies. Native image depends on this static library libz. So you wanna, so the first time using native image Ubuntu may fail due to the missing library. So here's an example. I installed Ubuntu, I installed GraalVM native image, I created this HelloWorld very simple Java application. I used the Java compiler to compile it to a class file, and then I used the native image tool with the GraalVM to compile the class file to the native executable. As you can see, the first time I ran it, it was successful until creating image, and it gave me a fatal error. Java lang runtime exception. There was an error linking the native image. Linker command exited with 1. And so the compilation was successful, linking failed. And the reason linking failed because linker not only combines your application, the binaries, but it also tries to grab all the dependencies. And one of the dependencies of the native image on Linux is libz, right? So you have to and you see, based on the linker command output, possible reasons for this include: it appears as though libz.a is missing. Please install it. And the way you install it on Linux, you say sudo apt. This is the application manager. Install zlib1g. So this is dynamic libraries for runtime. So, but we are doing compilation, which is, this is a development time. So you have to use also install the sudo apt install zlib1g-dev. So if you just install zlib1g, this is for the runtime, only dynamic libraries to, if an application requires this library at runtime, right, then this installation is enough. But we need zlib for the development time when we want to actually grab the code from the dynamic library. That's why you also need to install the dev version, right? Sudo apt install zlib1g-dev, a static library for compile time. And then linking happens after the compilation is finished, right? So the compiler here was successful, but once we are creating image, which means we are combining all the binaries to create a native executable file, the linker failed. All right. But once you basically install this dependency, rerun your application, and it's going to be successful. So let's head to our Ubuntu. And then I am going to create a new directory. Let's call it test on my desktop. Let's open this up. Let's see if we can open in terminal. All right, so I've also installed fish on top of my shell command in Linux. So again, my recommendation is to install the fish, which is very nice. So we're going to touch hello world Java. It's going to create an empty file, and then we're going to open it with the text editor. And then let's say public class hello world. And then we're going to say public static void main string args, right? And then system.out.println hello world from Java in Linux Ubuntu. And then exclamation mark, and then close the brackets, or close the double quote brackets, and then semicolon. All right. So this is all we need, and then I'm going to say that Graal home bin and then Java C -cp here, right? We only have one class, and then hello world.java. So actually we should have saved this first. Oh yeah, it failed because we didn't save it. So now again, okay, we have a typo. A string. So save again. Okay, let's pull up the directory. Let's clear this one and then run this. So I'm compiling with the GraalVM Java C, and let's check to see which version we're using. -- version. So 17.3. Let's see what native image we're using. Okay, actually, let's see what Java JVM we're using. Java -- version. So it's 22.1.0. This is the most recent version of the GraalVM as of the time of recording this tutorial. Now we have the class file. Now, obviously, the very first thing that we should always do run our Java application using the JVM, using the Java command to make sure everything works fine. Now it works fine. Obviously, the last thing is to go ahead and compile our Java application to native executable binary -cp here, and then hello world. We don't specify the dot class, and then the name of the output my app. All right, so it's going to take a little bit of time because I'm running on a virtual machine. Generating my app executable, and it also tells you, if you click on this terminal is very intelligent. It takes you to opens the Firefox, and then it takes you to these websites to give you more information about what does it mean that this application executable. This GraalVM native image takes you to, for example, the native image home directory for the documentation. Version info GraalVM 22.1.0, C compiler GCC. This is a Linux compiler. This is the default toolchain, and garbage collector serial GC, right? So when our application is compiled, there is a serial GC that does the memory management for our executable binary, right? Remember, even when you write a C++ application, you have to do the manual. Your application is responsible for memory management, right? Operating system is not. Operating system only manages the stack memory. It doesn't care about managing the heap memory or anything that is not allocated on the stack. So code area, everything succeeded. Desktop, my app, and then build artifact. Let's wait a little bit. Okay. Now we have the my app here, my app build artifact. And then what we're going to do, let's clear up, and then // my app. and hello world from Java in Linux Ubuntu. Let's go to the desktop, come back up here. It's about 12 megabytes, so it's a pretty large size compared to your class file, which was only 400 bytes, not even 1 kilobyte, half a kilobyte versus 12.5 megabyte. But by today's standards, 12.5 megabyte is pretty much nothing. So if we open this text file, it just tells you what kind of artifact we generated, which is let's see, so executable, and what was the name of the artifact? My app. All right, now I want to show you so even if we don't specify this hyphen cp, it still works fine because we are in the current working directory, right? So again, the class path here has the same meaning as the Java class path that we always use. All right, so back to PowerPoint. Let's look at, again, this is the output of the GraalVM in Linux. I'm running it in the fish terminal, which is a very colorful terminal. Starting compilation process, GraalVM version, information about classes, very similar in macOS, Linux, and you will see that later in Windows. The output is more or less the same. Performing static analysis, which classes packages require the most static analysis and compilation, the path to the generated native image, executable binary, and eventually we say that / the name of the executable. Now, if you don't specify the name of your executable, it's going to be the name of your class, and all letters are lowercase. In my example, I actually specified the name of the output file, which was my_app. Here, I'm not specifying the name of the output file. So by default, it's going to be in the name of the class, all letters lowercase. So I hope you enjoyed this lecture and now have a better understanding of the native image. Please stay tuned and I'll see you in the next one.